Hello, everyone. In this video, we'll be covering 15.8, which is another extension of polar coordinates to higher dimensions. In 15.7, we saw cylindrical coordinates. So now that was kind of polar coordinates in 3 dimensions, where we had regions kind of centered around an axis. Now we're going to have spherical coordinates, which are going to be a version of polar coordinates where, once again, we're centered around the origin. Okay, and I'll explain what that means as we go. So let's just dive right in and explain what spherical coordinates are. Okay, so spherical coordinates, if I have a 3-dimensional plane, spherical coordinates are just another way to label a point, to give the coordinates of a point. Okay, so we're used to the Cartesian, x, y, and z, and then we saw in the last section cylindrical coordinates, where we had what? We had r, theta, z, where these two were polar coordinates for this horizontal plane, and then we had just a z coordinate giving us our elevation. Okay. Now we have spherical coordinates. They're very similar to polar coordinates and cylindrical coordinates. So let's talk about what each of these elements represents, each one of these coordinates. Okay. What's theta? What's this angle theta? Or, well, what is this coordinate theta? It's an angle. And if we have, let's go ahead and draw a little 3D plane again, or 3D space. Okay. And this is my positive x-axis. This is my positive y-axis. This is my positive z-axis. And I have some point. Say, it's here in 3D space, and it kind of makes that. If I drop it down to the horizontal plane, it kind of makes this angle. Okay. Well, what's theta? Theta is the angle we make with the positive x-axis, just like polar coordinates. Okay, so that's my theta. Okay, what's my phi? Okay, this is the Greek letter phi, phi. That is going to be the angle we make with the positive z-axis. Okay, so this angle. And then what's my rho? This is not a p, it's the Greek letter rho. It's the length. It's the distance from the origin. Okay, so let's draw this a bit better. Okay, draw it a bit bigger, get a bit better view. Okay, so again, let's say I have this point hanging out in space, and that point, if I dropped it down to the XY plane, maybe it would be there. Okay. So this is my point. Once again, this angle here is my theta. Okay. And imagine I draw a line from my point straight to the origin. Okay. well, this angle that that line makes with the positive z-axis, that's going to be my phi. And then this length here is going to be my rho. Okay. So again, I can this is a perfectly valid set of coordinates. I can represent any point in this three-dimensional space with three coordinates of these forms. Okay, some restrictions on our coordinates. This distance between the point and our origin, we could think of it as radius. That's always going to be positive. So we're never going to deal with negative radius. A bit of a change from polar coordinates, right? In Calc 2, we had negative radius and negative angles, things like that. But here we're going to just keep it a bit simpler. Rho is always positive. That radius, that distance is always positive. And then phi, what's the restriction on phi? Phi is always between 0 and pi. Okay, so that might seem weird. Maybe the natural impulse is to think that this phi should be between 0 and 2 pi, right? Because we're dealing with circles and et cetera, et cetera. But really 2 pi is unnecessary. Think about it like this. I want to draw some point in my space. Okay. You know, if my phi is between 0 and pi over 2, all right, pi over 2 is this angle, right? So like my mental protractor can be, you know, I can have angles here, here, that's all between 0 and pi over 2. So that would give me all my stuff in my upper half of the space, right? And then pi over 2, you know, pi over 2 to pi would be like angles like this, angles like this. And so that takes me to the bottom half of my 3D space, right? So if my phi is between 0, which would be kind of pointing straight up, an angle pointing straight up, and pi, which would be an angle pointing straight down, that's going to really cover all my possibilities, right? Combined with the fact that we're, you know, allowing our theta to be between 0 and 2 pi, and then our radius is positive. Okay, so you got to get used to these coordinates. So I'd try plotting some points. Take this back for a second. So I'd try plotting some points. So for example, this point here, 2 pi over 4, 7 pi over 6. What would that look like? Well, we know our radius is 2, our angle with the x-axis is pi over 4, and then our, and this is, let's see, about 5 pi over 6. We don't want our angle phi to be greater than pi, right? So let's say phi is 5 pi over 6. Okay, so what would this point look like? Well, let's see. I'm going to do my angles first. Okay, this is how I graph these points. I think I kind of make my mental protractors. All right. So let's say I have a protractor that's lined up with the x-axis. I'm gonna make my I'm gonna open my protractor up to the angle pi over 4. Well, what would that be? Pi over 4 is like 45, right? So, you know, maybe it's pointing out this way, right, you know, right in the middle of the XY plane here. Okay, so I got my pi over 4. All right, so I got this kind of image of pi over 4 here. And then my phi is 5 pi over 6. So I'm gonna like, imagine this angle makes a plane, makes a vertical plane with the z-axis, and that vertical plane is coming out this way and going back that way. Okay. Now I'm told my angle phi is 5 pi over 6. So I'm going to think about drawing, you know, my angle 5 pi over 6. Where would that be? Okay, it'd be down here. It'd be pointing down here, right? Maybe, let's see. This is since it's coming straight out of the page, this is kind of a bad example. Let's play this around a little bit, play around with this a little bit so it's a bit more clear. How about if theta was 7 pi over 4. And then we'll leave this as 5 pi over 6. Okay, so let's see. Once again, I'm opening my mental protractor. All right, where's 7 pi over 4? That's almost 2 pi, right? It's, let's see, 7 pi over 4 would be like this angle, right? Yeah, this will work a bit better, be a bit clearer. Okay, so that's my 7 pi over 4 in that horizontal plane. And then I'm confining myself to this kind of vertical plane that goes through this angle and goes through the z-axis, right? And then I'm making the angle 5 pi over 6 with the positive z-axis. So what's 5 pi over 6? Okay, that'd be like this, right? Okay. So now I know I'm along this angle. So think about it like this: your theta kind of gives you this plane that you're working with, and then 5 pi over 6 that gives you your angle that you're going to be along in that plane. And then how far down that line do we move? We move 2 units. So my point should be here. Okay. There we are. In the textbook, figures 2, 3, and 4 give some nice examples of spherical coordinates. These spherical coordinates, why do we use them as opposed to Cartesian coordinates? Because there are some cases where representing things with spherical coordinates is a lot easier. Okay, and in figures 2, 3, and 4, we can see some examples of those. Let me take a break for one moment to make sure I'm recording. Let me switch my Wi-Fi network though. Okay, I'm very paranoid about the quality of these videos. I don't want to be cutting out because of weak Wi-Fi. All right, so figures 2, 3, and 4 in section 15.8. If you have the textbook, take a check those out. Really, the power of these spherical coordinates is representing functions and regions that have some sort of spherical symmetry, meaning symmetry around the origin, okay, around this point in the center of our 3D space. So figures 2, 3, and 4 kind of give some examples of that. And this is sort of like figure 2 here. Okay, and what would be the coordinates of this sphere be? Let's say we have this 3D region here, and let's just think about the skin of this this sphere. Okay, well, it would just be the equation of that skin of that kind of sphere would be x squared plus y squared plus z squared equals 4. And what if I wanted to make bounds of integration for this region, right? What if I wanted to make bounds of integration for the solid sphere? X squared plus y squared plus z squared is less than or equal to 4. Okay, so what if I wanted to integrate a function on that sphere? Okay, how would I set up my bounds of integration? Well, let's see, we'd pick one direction to be our constants, right? So let's say we pick z to be our constants. Well, what are my constants? -2 to 2, right? Okay, and then I take cross sections along the z-axis. And what are those cross sections? they'd be circles, right? All right, I lay my circle down flat on the page. It looks something like that. Okay, that's what my cross section looks like. And then let's see, what is the radius of this circle? Well, it depends on what z I'm at, right? So this outer boundary is coming from the equation x squared plus y squared plus z squared equals 4. Okay, and then we're treating z like a constant. So let's say I want to do dy here. Then y would be between positive 4 well, let's see, and x would be 0, okay, for these bounds. So my y's would be between positive 4 minus z squared and negative 4 minus z squared. And then my x bounds would be what? Square root of 4 minus y squared minus z squared, negative 4 minus y squared minus z squared, I believe. Okay, I believe that should be correct. Feel free to check me on that. So somewhat complicated in Cartesian coordinates. What about spherical coordinates? What would my bounds of integration be for spherical coordinates? Okay, even though we haven't talked about how to integrate in spherical coordinates yet, we could still look at this and set up the bounds, right? It's very similar to the thought process we're using for Cartesian coordinates and cylindrical coordinates. So I look at the region, okay? I just look at the region and play with the bounds a little bit, okay? So let's see, I'm measuring everything. I'm relating all my points in spherical coordinates to that origin. So let's see, what would all those points be? Well, I want to cover the entire sphere. So let's see. If I'm at rho equals 2, theta equals 0, and phi equals 0, I'd be up at this point. And I basically want to cover all the points going this way, and then all those slices going this way, etc. And for all radiuses or all values of rho. So my rho coordinates would be 0 to 2. My phi coordinates would be 0 to pi. And then my theta coordinates would be 0 to 2 pi. Okay. So drawing or writing these spherical bounds down is almost immediate, right? It's much more simple than doing the Cartesian coordinates. All right, continuing. We have, again, I haven't taught you guys how to integrate in spherical coordinates yet. We're just talking about bounds at the moment. We're going to have to develop some theory for integrating in spherical coordinates. Just to reiterate, we kind of have 3 versions of this material that we've seen so far. We have polar coordinates, cylindrical coordinates, and spherical coordinates. Okay, so let's talk, maybe you're a little bit confused about what the difference is, right? So remember, polar coordinates is when we're integrating on a 2D domain, like integrating in the XY plane. So we have like a function of X, Y, and maybe we're integrating, you know, on some region, and maybe that region is like got some sort of symmetry around the origin, right? It's got this symmetry around the origin in the 2D plane. Well, that'd be a great time to use polar coordinates, right? Because writing a region like this is really easy using polar coordinates, much easier than using Cartesian coordinates. Okay, and then we move up to 3D, and maybe we have a region that's kind of centered around an axis, like centered around the z-axis, for example, like a cylinder. You know, that'd be a good time to use cylindrical coordinates. Why? Well, this z-axis, that'll be convenient to leave as Cartesian, a Cartesian coordinate. And then these cross sections are again going to have that circular symmetry. So we want to use polar coordinates for those. So if I use r, theta, z, my cylindrical coordinates, that should represent my region very nicely. Okay, so this cylindrical stuff's good for symmetry around an axis. Okay, along, like when we have this symmetry that goes along one of our axes. And then spherical coordinates, what are these good for? These are good when, well, again, we're in 3D. But now instead of having some sort of symmetry around an axis that goes maybe up and down or left or right or anything like that, we just have this kind of nice symmetry around the origin again. So around this point right here in the middle. So things like spheres, integrating on spheres, certain other shapes like cones, which we can think of as like kind of pieces of spheres that are like, maybe like that's a piece of a sphere with its top cut off. That would give us a cone, right? So cones will be good to do with spherical coordinates. Things like this that are really in some way centered around the origin. Those will be good times to use spherical coordinates. Okay. So we want to begin the process of, taking a function in Cartesian coordinates and converting it to spherical coordinates. Okay. Let's just work on, before we talk about converting integrals and functions to spherical coordinates, let's talk about the relation between just points, okay? So let's say I have this point in spherical coordinates, this yellow point, and it's got these coordinates here. And let's say I want to see how are these coordinates related to my x, y, z coordinates. Okay. Well, let's see. This distance from my point to my origin, that's my rho, right, in spherical coordinates. Okay, how do I write that distance in Cartesian coordinates? Well, it's just the square root of x squared plus y squared plus z squared, right? Whatever my Cartesian coordinates are, this distance will be that square root. Okay, so we see that rho should be equal to my square root of x squared plus y squared plus z squared. Okay, where x, y, and z are going to be the coordinates, x naught, y naught, z naught are going to be the coordinates of that point. Okay. Now let's say let's assume I'm given these spherical coordinates. What would my x coordinate be? Okay, well, let's think about this step by step. What is the x coordinate of this point here? Well, that x coordinate it's essentially this distance here, right? Along the x-axis that my point is. Okay, so now let's think about triangles. All right, what do we know? Let's see, this is my theta, right? And I'm given my theta in my spherical coordinates. Okay, so this x distance here, what is that? That would be the cosine of theta times whatever distance this is. Okay, we don't know this distance, but we could figure it out, right? So it's theta times whatever that distance is. Let's call that distance h. Okay, so my x is going to be whatever this distance is, h, times the cosine of my theta. Okay, so let's now figure out what h is. And to figure out what h is, we're going to look at a different triangle. Okay, so let's look at this triangle here. Okay. Well, actually, you know what? Instead of looking at this triangle, let's look at this triangle here. Okay. What am I trying to do? I'm trying to find this distance. Well, this distance from this point to the origin should be the same as this distance here. Okay. So if we can find this distance, that's the same thing as finding this distance. Okay. Now, why am I looking at this triangle, this triangle? I'm looking at this triangle because I know this angle. What is that angle? That's my phi. Okay. So then, and then I know this distance here. This is my, this distance here along this edge. My hypotenuse is rho. Okay. So if I know this is my rho, this is my phi, what is this distance here, which is the same as my h? Let's see, that would be rho times the sine of phi. And that is this length here. And that length is the same as this length. Okay. So that h, that distance here, is rho times sine of phi. So my x would be rho sine of phi times cosine of theta. Okay. We can do a similar process for my y coordinate. Okay, what's my y coordinate? What's the y coordinate of this point here? Well, remember, y coordinate is just what? This distance, right? Okay. And to make it easier to compute, this distance here is the same as this distance, right? Okay. Well, what is that distance? It's going to be this length times the sine of theta. Okay, and we already know what this length is, right? We said it was what? Rho times sine of phi. So y should be rho sine of phi sine of theta. Okay, and finally, we want to know the z coordinate. Well, what is the z coordinate? Let's see. The z coordinate is this distance. Okay. Well, let's see. What is that distance? I know this length is rho. This angle is phi. So that distance should be rho times cosine of phi. Okay. So now I see how my Cartesian points relate to my spherical points. So let's see an example. Let's convert these spherical coordinates to Cartesian coordinates. Okay. And all I need to do is plug my values for rho, theta, phi into these expressions. Okay, so what's my x going to be? My x is going to be rho 4 times sine of phi, so sine of pi over 6 times what? Cosine of pi over 6. Okay. So what is that? That's 4 times what? 1/2 times square root of 3 over 2. So square root of 3. What's my y coordinate? My y coordinate is rho times sine of phi, so sine of pi over 6, times sine of theta, so sine pi over 6. So in other words, 4 times 1/2 times 1/2, 1. What's my z? My z should be rho, which is 4, times cosine of phi, cosine of pi over 6. So that's 4 times square root of 3 over 2, so 2 square root of 3. So it looks like my x, y, z coordinates would be square root of 3, 1, 2 square root of 3. Okay. All right, so now we've seen some Cartesian coordinates derived from these spherical coordinates. We've seen how these spherical and Cartesian coordinates relate to each other. We've seen how to draw, plot a point in spherical coordinates. I would suggest looking at that figure those figures 2, 3, and 4 I already mentioned. They give some good, if you can kind of play with those in your head, you can get some good intuition on how these spherical coordinates work. So, for example, what would just the sphere be in spherical coordinates? So let's say I have a sphere centered at the origin of radius, 4. And I'm just talking about the skin of that sphere. I'm not talking about like integrating on the region, the 3D region. I'm just talking about how can we write that sphere in spherical coordinates? Well, this would just have the spherical equation rho is equal to 4, right? If rho is equal to 4, if this is my equation, then I'm saying, okay, my radius is 4, and my my theta and my phi can be anything. Okay, so if I take all possible combinations of radius 4 and theta and phi, what do I get? I get all the points on the surface of my sphere. Right? Similarly, what if I just have written phi equals pi over 4? Okay, that's like saying, okay, the only condition I have is the angle with the vertical axis. Okay, so that I'm saying that angle is pi over 4, and then my radius and my the radius and my theta can be anything. Okay, so what would that give? So remember, we're dealing with these restrictions that my radius, my rho, is greater than or equal to 0, but I'm not given any upper bound here. And then my theta, think about it. You can think about it between 0 and 2 pi. That'll give you all possible angles, right? Okay, so if I think about all possible combinations of this stuff, what do I get? maybe you can see, I'm going to get a cone centered around that vertical axis. Okay, and it's going to extend up forever. Okay, so again, this is a very simple equation, right? The equation for this cone is just this. Compare that with the Cartesian equation, which is, you know, what we saw equation for something like this in 12.6, and it was, you know, more complicated. Okay, so play with those a little bit. Now let's start talking about integration with these spherical coordinates, which is really what we're concerned with. We're developing this stuff to give us another tool of integrating on three-dimensional domains. So let's begin talking about integration on these spherical coordinates. So how did we develop this for Cartesian coordinates? Remember, we started by thinking about Riemann sums. So maybe we're integrating on a 3D domain. What did we do to the 3D domain? We chopped it up into boxes, right? Where our x coordinate was between some, you know, points A and B. My y coordinates were between C and D, and my z coordinates were between E and F. Okay, that gave us one particular box, right? And I found the volume of that box, this delta V. Okay, let's say, you know, these, I chopped this domain up into several boxes. I look at the volume of each little box, delta Vi Jk. Okay, well that's what? It's the length of our little box times the height of our little box times, you know, the depth of our little box, however you want to label those dimensions. And then we multiply it by a functional value, right? And that gives us this Riemann sum, this triple sum. And then we take the limit as the volume of this box gets smaller and smaller and smaller, and that turns into a triple integral. Okay. Now we saw, we did something similar for cylindrical coordinates, where we saw that, you know, this volume here of our 3D region, it wasn't as simple as just multiplying a length times a width times a height. We need to have this kind of term, this extra term that gets included in our integral, right? And we're going to see something similar with spherical coordinates. So really, we want to just we want to start by figuring out what is the volume of a little box like this for spherical coordinates. Okay, so let's think about this, the version of this in spherical coordinates. So first of all, instead of having x less than or equal to a, or excuse me, greater than or equal to a, less than or equal to b, etc., we're gonna have similar condition for our spherical coordinates, but it's going to give us a different shape, right? So my rho is less than or equal, or excuse me, greater than or equal to alpha, less than or equal to beta. My theta is less or greater than or equal to gamma, less than or equal to delta. And my phi is greater than or equal to epsilon, but less than or equal to zeta. Okay. Now, what kind of three-dimensional shape does this give? It gives us one of these wedges, okay, which is circled around think about it as like a chunk of a sphere, basically. It's, and if we took all of them, basically what we're doing is we're like starting with a sphere and then we're taking chunks out of it. Okay. So what are we dealing with here? Okay. You know, okay, think of this as the side, these lines as giving me the sides of this wedge. Okay. This side of the wedge is what? Theta 1. And this side of the wedge is theta 2. Okay. Or, you know, let's see, what did we say about our theta? Theta is between gamma and delta. Okay, so I could think of this angle as gamma and this angle as delta over here. And then let's see, my rho is between alpha and beta. Okay, well, my object starts here at this radius, which is alpha, and then it goes this far back to this angle, or to this radius beta, this rho beta. All right, and then we're talking about angles with the, our object goes like this. This angle, let's see, these are angles with the z-axis. Okay, so maybe this angle would be my epsilon, and then this angle would be my zeta, however you draw zeta. Okay. All right, so that's kind of what a chunk, one of these kind of wedges would look like. That's the kind of shape I get when I have bounds like that in spherical coordinates. Okay. Now, if I'm integrating on some bigger region, like if I'm integrating on the sphere, essentially what I want to do is I want to chop my sphere up into a bunch of wedges like these, and then I multiply my function value. My function value on that wedge times the volume of that wedge. And then I add up all the values of those wedges. And that gives me my Riemann sum. And then I take the limit as those wedges get smaller, right? So that's the idea. So this function is not really a problem. Okay, what's the problem is we need to find the volume of each of those wedges. Okay, so let's think about the volume of one of these individual wedges. Okay. Now we can think of this wedge as approximately a box. It's got some curvature to it, but we could estimate it with a box. Okay. So think about, let's pretend these are nice straight edges, where I have like a straight edge there, a straight edge going this way, and then a straight edge going this way. Okay. All right, so if I know those three lengths, I can multiply them together to get my volume of my box. Okay. All right, well, let's think about the lengths of those three sides. Okay. This side here is probably the easiest, right? Remember, we're measuring, maybe we have our origin over here, and then, whenever we get our 3 dimensions. Okay, I'm not going to draw the axes. Let's say this is my origin. Okay, what are the coordinates of this box? Well, let's see. First of all, I got my my radius 1 here. That's where my object begins. All right, to my radius 2 here. Okay, so call that distance. Call this distance your delta rho. Okay, and so delta rho there. That's pretty easy. All right, so that's one of the sides of my box. All right. What about this side? Okay, what's the length of that side? Well, don't think of it as forget about the wedge for a second. Think of the kind of 2D. Think of this in 2 dimensions for a second. Think of this as the sector of a circle, right? What is this piece of circumference? How long is that? It's the angle times my radius, right? What radius? I'm just going to use this inner radius here. Let's call it rho 1. Okay, so this inner distance here is whatever this angle is, and I shouldn't have written as theta. I should have written it as, let's call it whatever. Let's call it omega. How about that? So this distance here is let's call it this rho 1 times whatever this angle is, this omega. All right, well, what is that angle omega? If I have my vertical axis here, remember this angle omega is equal to phi, let's call that phi 1, and let's call that phi 2. Well, then omega is phi 2 minus phi 1. In other words, delta phi. Okay, so that means this length here is approximately rho 1 times delta phi. Okay, now I'm just, instead of like, you know, let's see, we're kind of making this a box, and this box is a little weird because it's got two different lengths on, like this side is one length and this side is another length. We're just going to use this shorter side, this inner side. Okay, and that's why I'm writing it as phi 1. All right. So let's see, we've said this is delta rho. Oh, this side's delta rho. This side is delta phi times rho 1, or that is rho 1. All right, what are we missing? We're trying to find the volume of a box. We would also like to know what this length is, right? Okay, what's that length? Well, it would be it's going to be this term. Okay, how does that relate to what I've drawn here? Okay, essentially what I want is I want this distance. Okay, what is that distance? You might think it's, well, let's see. Let's relate it back to the origin again. Okay. So once again, think about all this in relation to our origin of our 3D space. Okay. Okay, what is that distance there? Well, we could think of it again as the sector, the piece of circumference of a circle. Okay, so the question is, what is this angle? Let's call it omega again. What is that angle? And then what is that radius? Well, the angle is going to be, okay, if I have my 3D plane, okay, that angle is going to be theta 2 minus theta 1. Okay. Or in other words, delta theta. Okay. And then I need to measure this distance here. Okay. Now, you might think it's just the radius, but that's not quite right, because really that distance is the distance projected down onto the horizontal plane. So think about the XY plane, or the horizontal plane. Okay, maybe this wedge is kind of above the horizontal plane. So I think about all this projected down onto the horizontal plane. Okay, and this is really the distance I'm looking for in that horizontal plane. So the I have this angle theta 2 minus theta 1, and then I need to measure, I need to multiply it by whatever this this distance is in the xy plane. Okay, so I just care about this xy distance. Okay, in the horizontal plane. Well, what is that distance? It is going to be the actual radius, this rho, times the sine of this angle here, sine of phi 1, which I guess would actually be this angle. Again, which angle I'm using doesn't really matter. Let's call it this one. Okay, so this distance here is rho 1, this radius, times sine of phi 1. Okay. Now my drawing lacks a lot. There's a lot to be desired there. So check out the textbook. The textbook gives us, pretty much the same figure, but it's a bit more cramped. But maybe you can see more clearly the orientation of everything. Let's see, figure 7 in the textbook. There's a lot going on in that figure. So that's why I've kind of tried to do it one step at a time. But I think if you watch this video and look at this figure kind of in conjunction, maybe it'll make a lot of sense. Okay, so we see the three sides of our the approximate lengths of the sides of our box, right? Okay, so we're approximating the volume of this wedge with just by multiplying the three sides together. Okay, and we can talk about why this works in a second, but once again, those three sides would be what? Delta rho. Okay, this side, rho 1 times delta phi, which would be what? This side. And then rho 1 sine of phi 1 times delta theta, which would be this side. Okay, we multiply those sides together, and we get roughly the volume of the wedge. Okay, and then just rearranging the terms. I got two of these rho 1s right here, so I'm going to combine them into rho 1 squared. I have this phi 1. Okay, I'm going to move that there, and then I just have my delta rho, delta theta, delta phi. Okay, so the Riemann sum. Okay, the volume of this this volume here is approximately this. Okay, so when I set up my Riemann sum, this f of my whatever my coordinates times my volume. Okay, what is my volume? My volume is this thing. Okay. Don't worry about the indexing too much. Remember, this is just I have a bunch of boxes, a bunch of these wedges. So this I, J, and K just refers to a bunch specific wedges. And I have my function value on those wedges, and I have my volume of my wedges. Okay. Now, I said we could talk about why we could use phi 1 and rho 1 and phi 1 instead of rho 2, phi 2, et cetera, et cetera. Well, as our wedges get smaller and smaller and smaller, those values become pretty much the same thing, right? Like if I have this wedge, there's not much difference between rho 1 and rho 2, and there's not much difference between phi 1 and phi 2. And then really what we can do is kind of use a mean value theorem, where this we can use mean value theorem to, instead of saying like, okay, we're going to use this rho 1 or rho 1 and phi 1, we get mean value theorem just gives us some rho along here and some phi along here. Okay, and it just works out. Now you can look at the textbook if you want to, a bit more of an explanation. There's not too much more of an explanation. Okay, but check that out if you like. But really, this is an approximation to our volume, and then just think that as the wedges get smaller and smaller and smaller, this approximation becomes better and better and better. Okay. So when we take the limit of our Riemann sum, our triple sum, what happens to each of these elements as we take the limit of this volume going to 0? Well, as we've seen many times before, my summation signs become integral signs. My functional values, or my functional values here, my function at these coordinates, these coordinates, I'm taking an element of each wedge, and then as my wedges get smaller and smaller and smaller, I'm essentially taking all my my function of all my values. Okay, and then I have this rho term here. Well, that's just going to become rho squared. I have this sine of phi, and that's just going to become, that becomes sine of phi. And then I have delta rho, delta theta, delta phi. Well, that becomes d rho, d theta, d phi. Okay. All right. So what's going on here? I'm trying to integrate some function on my three-dimensional domain. When I integrate that function, I plug my function into my integral. I have my d rho, d theta, d phi, but I also have this rho squared sine of phi term. Okay, and this is very similar to the cylindrical coordinates. Remember, in cylindrical coordinates, when I integrated the function fr, f theta, fr theta z, I plugged this function to my integral, but I also had r dr d theta dz, where I had this extra r term here. Same thing's going on here with my spherical coordinates, but instead of r, I have this rho squared sine of phi. Okay, so whenever we integrate a function in spherical coordinates, we need to multiply the function by this rho squared sine phi term. Okay, so let's see an example. Integrate rho cubed plus 3 times theta on the region in the first octant bounded by this sphere, and that should be an equals. Okay, so what does this mean? Okay, first octant, what is that? Well, that's this part of the 3D space, right? And then bounded by x squared plus y squared plus z squared equals 9. Well, what is that? That's the sphere with radius 3. So the first octant, let's say inside the sphere in the first octant would give me this kind of blue shape, right? It's basically 1/8 of a sphere. Okay, so I want to integrate this function on this blue region here. Okay. Well, let's set up our integrand first. Let's set up the stuff inside the integral. Not worry about the bounds for a second. Okay, what is my function inside the integral? Well, my function is already in terms of spherical coordinates, so I just write this down. Okay, and then let's see, I need to multiply by my rho squared sine of phi. Then I have my d rho, d theta, d phi. Okay, so that's my integrand. What are my bounds for my integral? Okay, when we're finding these bounds, we really just have to look at the region and think about it in spherical coordinates. Okay, so what are the bounds of this region? Okay, they're all gonna, all these bounds are going to be constants for this integral. Okay, so what are my bounds on? Let's see, what am I doing here? Let's do from the inside out. Okay, so what are my bounds on rho? Okay, where my radiuses begin and where do they end? Okay, so think about like moving along this line here. Okay, my radius would begin at my rho would begin at 0 and go till whatever this value of rho is. Well, that outer edge is given by sphere with radius 3. So this would be radius 3 here. So my rows go from 0 to 3. All right, what about my thetas? Okay, where do my thetas begin? Where do they end? Okay, my region starts here, rotates this way until, let's see, I hit this axis, right? So what angle is that? That's pi over 2. Okay, so I start at 0 and go to pi over 2. Okay. What about my phi? Where do my phi start? Well, remember, I'm measuring my phi from the positive z-axis down. Okay, so where does it start? I could think of it starting here at 0, and then I go down until I hit pi over 2 again. Okay, so that's my integral. Integrating, let's see. I'm going to multiply, I'm going to combine these terms, integrating in terms of rho first. So I have what? Rho to the 5th plus 3 rho squared theta sine phi d rho d theta d phi. Okay, integrating in terms of rho, I get rho to the 6th over 6 plus rho cubed. Okay, from what? 0 to 3. Let's see, that's kind of ugly. What's 3 to the power 6? 27, 81, 243, 7, 39, something like that. Let's see, 243 times 3, 9, 12, 7, 729. Okay. So 729 over 6. So let's see, 243 over 2, something like that. Plus 27. Okay. So whatever that is, let's see, I could do 54 over 2, and then this will become 297 over 2. Okay. Okay, so just a constant. Times theta times sine of phi, and then I'm integrating in terms of theta next. Okay, theta becomes, let's see, I'll go ahead and pull out my constant. I integrate in terms of theta, I get theta squared over 2, evaluated from what, 0 to pi over 2. So pi squared over 8. Okay, and then I integrate sine of phi in terms of phi. And then I get, let's see, times negative cosine of phi from what, 0 to pi over 2. Let's see, this would be what, 1? Okay, so that should be my final answer. Quick mental math, so I might have made some mistakes. Let me know if I did. All right, so the moral of the story is when we're integrating a function in spherical coordinates, we need to multiply the function by this term always. And we're going to see the same thing when we convert from Cartesian to spherical in a few moments. Okay, and then finding the bounds, we just have to think about the region in terms of spherical coordinates. Okay. So now let's start thinking about converting from Cartesian to spherical, which is the tool we want to develop, right? We don't normally just, we're not normally just given a function in terms of spherical coordinates and told to integrate it. Usually we're starting with a Cartesian equation and we notice some sort of spherical symmetry around the origin, and we think to ourselves, hey, it's probably going to be easier to integrate in spherical coordinates, and so we convert. Okay, that's kind of the context for this tool. So how do we take a Cartesian integral like this and convert it to spherical coordinates? Well, going all the way back up to when we were just talking about spherical points and spherical coordinates, when we had, these relations. Okay. Basically, I'm just going to replace the x with my function, the x in my function with what? Rho times sine of phi cosine of theta. I'm going to replace the y's with this, and then I'm going to replace the z's with this. Okay. I'm going to replace my dx, dy, dz with what? Rho squared times sine of phi. I have that term I need to multiply by. Then my d rho, d theta, d phi. Okay. So rewriting the integrand, really it's just, there's no difficulty here. It's just remembering these three things, well, these four things really. And then it's just plug and chug, right? You just plug it in, you just replace it. Okay. Now, if this was a face-to-face class, maybe there would be some challenge in remembering all these, right? But since this is online, you can write these down on note cards. You can keep them right next to you whenever you're solving problems, even on the test. So there shouldn't be any problem there. Okay. The challenge will, as always, be with finding the bounds. Okay, the bounds. There's no memorization. Oh yeah, you just do this. You have to be able to visualize that region or draw that region, and you need to be able to look at it and find the bounds. Okay, so let's get a little practice. So let's say we want to integrate x squared plus y squared on this region E, where E is the region between these two spheres, x squared plus y squared plus z squared equals 4, and x squared plus y squared plus z squared equals 9. Okay, so the sphere with radius 2 and the sphere with radius 3. Okay, so let's say I want to integrate this function on that region. Okay, and let's see, I got a couple examples. Well, converting the actual integral isn't too tricky, right? What did we say we do? I replace x squared with rho sine theta, sine phi cosine theta. Okay, so I replace x with that. I replace y with rho sine phi sine theta. All right. And then my this would be in Cartesian, this would be dx dy dz. I replace the dx dy dz with what? Rho squared sine phi, and then d rho d theta d phi. Okay. Let's try and squeeze all this onto one line. Okay, so the integrand, the stuff inside the integral is pretty easy, pretty immediate. Okay. This looks a little messy, but it's not too bad. Let's go ahead and simplify it before we look at the bounds. So let's see, I got a rho squared here, and I got a rho there and a rho there. So let's see, I can factor out all those rows as a rho cubed, all right? Oh wait, this because this term's squared and that term's squared. So let's see, we could factor out a rho to the 4th. And then what do I have? I have sine phi squared cosine squared of theta plus sine squared phi sine squared theta sine phi d rho d theta d phi. Okay. Factor out the sine squared of phi for both of these. And so we've got another sine phi there. So we can rewrite this as rho to the fourth sine cubed phi cosine squared theta plus sine squared theta du rho d theta d phi. Well, this is just 1. Cosine squared theta plus sine squared theta, that's just 1. So that simplifies matters a lot. We have rho to the fourth sine cubed of phi d rho d theta d phi. Okay. All right. Now you might, be jumping ahead and thinking about how to integrate sine cubed of phi and rho to the fourth, etc. But let's take a little break here, and before we start integrating stuff, let's find our bounds. Okay. Okay, so what is our region? Remember, our region is the region between the two spheres. Sphere of radius 2, sphere of radius 3. Okay, so quickly. Okay, I have a sphere of radius 2. And then I have a sphere of radius 3. So my region is inside the blue sphere, outside the white sphere. Okay. Boom. Well, just, I've drawn circles, but keep in mind these are supposed to be spheres. Okay. All right, so what are my bounds for that region? Okay. You just have to pick one and kind of try and, start from there. Okay, so let's pick, let's see, what have I written down first of all? D rho, d theta, d phi. Let's see, let's try and do it from the inside out, okay? For the simple triple integrals like this, we can kind of figure out our bounds in any order usually. Okay, if it's a bit more complicated, maybe we have to be a bit more systematic and kind of work from the outside in, something like that. But this integral should be fairly straightforward. We could probably find our bounds in any order. Okay. Think about your rows first of all. Maybe that's simple. Okay, where does my region begin? Remember what the region is. Okay, the region is inside between the two spheres, right? Okay, so it's this region. Okay, so where do my radiuses begin? My rows. They begin at this rho equals 2 and they stop at this rho equals 3, right? Okay, so it looks like my row bound should be 2 to 3. What about my, let's see, what's next? My thetas. Well, I've drawn circles here, but remember, these are supposed to be spheres, right? So the sphere wraps all the way around, right? Okay, so it looks like my theta bounds should be 0 to 2 pi. Okay, what about my phi bounds? Well, remember, phi is between 0 and pi, right? So if my phi is like 0, then I have this point. And then if it's like maybe pi over 4, I have, this kind of axis or whatever. And then I'm drawing, I have all these phis as well, all the way to pi. Okay. So it looks like my phis should be 0 to pi. Okay, so those are my bounds. And now let's go back to our integral. Okay, I want to integrate this thing on those bounds. Okay. If you haven't picked up from the cylindrical coordinates, okay, maybe it's clear now. Excuse me. With these cylindrical and spherical coordinates, the trig stuff's pretty important. So this is going to be from like section 7.2 of the textbook, I believe, Trig Integrals. Okay, so how do I integrate sine cubed? It's not a U substitution. It's not a trig substitution. I mean, I guess it is a U substitution, but it requires a little trick. When I have this sine cubed, I split off one of the signs. I split off one of the signs. I write the sine squared as 1 minus cosine squared. And then I do a u substitution. U equals cosine. Du equals what? Negative sine. And then my integral becomes let's see. I was integrating. I was supposed to integrate in terms of rho first, but let's go ahead and just, everything's constants over here. So we still have Fubini's theorem, so we can just switch the order of integration without worrying about it. So let's say I was instead doing this, okay? Just so I can get that sine cubed out of the way first. Okay. So I've converted my phi's into these u's. Okay. I've made a u substitution that makes this easy to integrate. So let's see, I end up with rho to the fourth u minus u cubed over 3 for bounds. I'm going to undo my substitution. What were my phi bounds? Messed that up. Let's see. I didn't change my bounds when I changed the order of integration. So my phi bounds are 0 to pi. Let me clean this up a bit. Okay. Plugging in my values. Let's see, cosine of pi. What is cosine of pi? That's -1 minus cosine cubed of -1, or excuse me, -1 cubed. Okay. Minus what? 1 minus 1/3. Let's see, so I have rho to the fourth times, let's see, -2/3 minus 2/3, so -4/3. Then d theta, d rho. The rest of the integrals are easy. Let's see, I pull out my constant, -4/3. I integrate in terms of theta next. Well, there are no thetas, so it just becomes -4/3 times 2 pi times the integral 2 to 3 of rho to the fourth d rho. I integrate in terms of rho, and I get what? Rho to the fifth over 5 times -8 pi over 3. What's 3 to the power 5? What did we say? Let's see, 3 to the third is 27. 81, 243. So 243 over 5 minus what? 8, 1632 over 5. So that's what? 211 over 5 times negative 8 pi over 3. So you kind of simplify that. Doesn't seem like it. So how about 1688 over 15 pi? All right. Seems like this is my answer. Let's see, this was number, which one? 23 from the textbook. Let's see if that one was correct. (1688 pi over 15). Excellent. That was a little nerve-wracking. Whenever I do a long problem, I'm always paranoid I've made some mistake, like the rest of you, I'm sure, and I have the added pressure of trying to do this in one take and not look like an idiot. All right, let's do one more example. So let's integrate y squared z squared on the region E, where the region E is above the cone pi over 3, phi equals pi over 3, and below the sphere rho equals 1. Okay. All right, so this is interesting. We're given a region. Our region is given to us in spherical coordinates, so that's nice. We don't have to like convert our region from Cartesian. We don't have to convert our surfaces from Cartesian coordinates to spherical coordinates. Okay, so that'll help. So again, let's begin by, and this is also in the book. I think this is like number 22 in the book, but I don't have the even solutions just like you. I think this is number 22. So let's work it out, but I guess we'll just have to trust me on whether it's right or not. So first, converting the integral. Let's see, y, we know y is what? Rho sine of phi sine of theta, right? So that y squared in our integral should become rho sine of phi sine of theta squared. And what's z? Z is, what do we say? Rho times cosine of phi, I believe. So rho cosine of phi squared. Okay. And then I need to multiply by my my dx dy dz becomes what? Rho squared sine of phi d, whatever order we do it in. It's called d rho d theta d phi for now. Okay. Okay, so let's go ahead and multiply, factor out the rows and make everything look nice. So you have rho squared here, rho squared here, rho squared here, rho to the 6th. Okay, sine squared of phi. I have a sine squared of phi here, a sine of phi here, so I get sine cubed of phi. Then I have sine squared of theta here, and a cosine squared of phi there. Okay, so it looks like I have got all my terms, and then I just have my what? D rho, d theta, d phi. Okay, I'm going to go ahead and switch these two around just so I have all my phis kind of next to each other. Oh, and I've already forgotten what they were. All right, sine squared of theta, cosine squared of phi. Okay, so it looks like this is my integral. Okay. All right, so I have this integral, and let's go ahead and find our bounds. Okay, so we have a region above the cone, phi equals pi over 3, and below the sphere, rho equals 1. Okay, so let's try and draw our region. Okay, so what's the cone? Pi over 3. Phi equals pi over 3. Okay, well, remember, this is kind of going back to figures 2, 3, and 4 from the book. Pi over 3, phi equals pi over 3 would be, you know, essentially this angle, okay? And the equation phi equals pi over 3, essentially I consider all the points whose angle phi is pi over 3. And what does that give me? It gives me a cone. Okay, and the cone actually goes up forever. Okay, all right. But we're also told, okay, our region is above the cone but below the sphere. All right, so we have this cone that goes up forever, but then we have the sphere, rho equals 1. Well, that's the sphere of radius 1, right? What does that look like? Okay, so rho of radius 1. Okay, so a sphere like that. Really bad sphere. Okay, and then I take those two conditions together, and I've drawn this kind of poorly. Let's draw this cone again. Let's do it in green. Okay. Okay. So with those two conditions, above the cone and below the sphere, what is that region? Well, it's this region inside the cone and below the sphere. Okay. Well, what does that give me? It basically gives me kind of like an ice cream cone, where the green, you could think of the green curve as the cone itself, and then the blue is the scoop of ice cream sitting on inside and on top of the cone. So I get this region like this. Okay. Let's go ahead and draw it all together. All right. So I want to integrate on this region. Okay, so what are the bounds of this region? Well, we have a lot of information just from these equations here. Okay. So let's think about our bounds. Let's see, what do we want to start with? Do we want to do d rho, d theta, d phi? Well, let's do some low-hanging fruit first. How about we start with d theta on the inside? Okay. What are my theta bounds? Well, this is this object wraps all the way around, right? It's maybe it doesn't exist in this region here, but it does go all the way around this vertical axis. So it looks like my theta bounds should be 0 to 2 pi. Okay. And then let's see. What are my my radius bounds? Okay. Well, let's see. Let's start at my origin and kind of think about my radiuses going outward. Okay. Okay, so my radiuses actually are just 0 to 1, right? This is this top of my object here. This is the sphere with radius 1, right? So if I'm thinking about my radiuses, they start at the origin and they they go until they hit that outer edge, which is just the equation rho equals 1. So my radiuses are just 0 to 1. My rhos are just 0 to 1. And then what's left? What are my phis? Okay. Well, think about your phis. Again, we're working on this region here in the interior of my cone. My phis would start here and go until the outer edge of this object, which is just pi over 3, right? It's coming from that cone. Phi is equal to pi over 3. So 0 to pi over 3. And those are my bounds. And then let's see, I need to plug my integrand back in. I'm integrating this thing, and let's see. Let's go ahead and rewrite this. 0 to 2 pi, 0 to 1, 0 to pi over 3. And what is that? That's d theta, d rho, d phi. All right. Last step, just integrating. All right, so integrating in terms of theta first. And again, by Fubini's, when everything's constants in here, when the bounds of my integral are nice, just constants, and my function inside the integral is of this nice form where I can kind of split it up into components of these coordinates, like this sine squared of theta, right? That only depends on theta. There's no phis in there. There's no rhos in there. Remember, there's this nice little shortcut where we could think of this as this integral is the same thing as integral of rho to the 6th d rho. What's my rho? What are my rho bounds? 0 to 1 times the integral of phi sine squared, or excuse me, how about sine squared theta? 0 to 2 pi d theta, and then 0 to pi over 3. What is it? Sine cubed phi cosine squared phi d phi. I could do this integral that way as well. It's the same thing, and it works out the exact same as kind of doing them as I did in the previous problem, where I kind of do this nested integral. We could do these 3 integrals separately, as long as it splits up nicely like this. Okay, so let's see. Let's call this A. Let's call this B. Let's call this C. Okay. Well, let's solve the A integral. Okay, rho to the 6th d rho, 0 to 1. Well, that is what? Rho to the 7th over 7 from 1 to 0 equals 1 over 7. Okay. How about the B integral? All right, sine squared of theta d theta. Okay, from what? 0 to 2 pi. Okay, again, trig stuff important here. I do my, what is it called? The double angle. This is sine squared is equal to 1/2 1 plus 1 minus cosine 2 theta. Okay, pull out the 1/2, integrate. I get what? Theta minus sine of 2 theta over 2 from what? 0 to 2 pi, right? Equals 1/2 times 2 pi. What's sine of 4 pi? That's 0. Okay, so 1/2 times 2 pi, pi. Okay. C integral. Okay, the C step. Sine cubed of phi, cosine squared of phi. D phi. And what, 0 to pi we said? Or no, 0 to pi over 3, right? Yep, pi over 3. Okay. This is again from that section 7.2 of the textbook. It's a trig integral. So we could say, all right, u equals, we could do this one. Let's see, what do we want to do? I could split off one of my sines to write this as sine squared of phi, sine of phi times sine squared of phi times cosine squared of phi. I turn this sine squared into a cosine squared, like so. Okay. Let's go ahead and multiply these together. And we get what? Cosine squared phi minus cosine to the 4th of phi. Make the u substitution, u equals cosine of phi, du equals negative sine of phi d phi. So my integral becomes what? Negative u squared minus u to the 4th du. Integrating, I get what? Negative u cubed over 3 minus u to the 5th over 5. Undoing my substitution. For my bounds, what? Pi over 3 to 0. Okay. Plugging in, let's see, cosine of pi over 3 is what? 1/2 cubed, 1 over 8 divided by 3, about 1 over 24. 1/2 to the 5th is what? 1632, 1 over 32 divided by 5, 1 over 160. Okay. Equals, let's see. Can I combine these fractions easily? 1 over 24 minus 1. Am I missing any? Nope, I don't think I'm missing anything. Let's see, 5. If I multiply by 5, I get what? 120. Yeah, it doesn't really combine nicely, does it? I guess, let's see, common denominator 8. So fractions, right? Let's see, this is 1 over 8 times 3, and this is 1 over 8 times 20. Okay. How about I multiply this by 20, this by 3. So let's see, 20 over 480 minus 3 over 480. Okay. So that should be my C integral, unless I've done something horribly wrong along here. All right, so I found my 3 pieces of my integral, and then I just multiply them together to get my solution. So what? 1/7 times pi times -17/480 should be my solution. But I guess we'll never know for sure because this was an even problem from the textbook. So unless I go and check out the solution manual from the math department, which I'm not going to do, we'll have to take my word for it. But work it out on your own and see if you get something different. Let me know. All right, so that is all the material from 15.8. There's plenty of examples, and you definitely need to practice setting up the integrals, but that is everything I can tell you about it. Good luck on the work.